one another. Fluids flow easily and conform to the shape of their containers. The geologic processes related to the movement of fluids on a planet's surface can completely resurface a planet many times. These processes derive their energy from the sun and the gravitational forces of the planet itself. As these fluids interact with surface materials, they move particles about or react chemically with them to modify or produce materials. On a solid planet with a hygrosphere and an atmosphere, only a tiny fraction of the planetary mass flows as surface fluids. Yet the movements of these fluids can drastically alter a planet. Consider Venus and Earth, both terrestrial planets with atmospheres. Venus and Earth are commonly regarded as twin planets but not identical twins. They are about the same size, are composed of roughly the same mix of materials, and may have been comparably endowed at their beginning with carbon dioxide and water. However, the twins evolved differently largely because of differences in their distance from the Sun. With a significant amount of internal heat, Venus may continue to be geologically active with volcanoes, rifting, and folding. However, it lacks any sign of a hydrologic system. There are no streams, lakes, oceans, or glaciers. Space probes suggest that Venus may have started with as much water as Earth, but it was unable to keep its water in liquid form. Because Venus receives more heat from the Sun, water released from the interior evaporated and rose to the upper atmosphere where the Sun's ultraviolet rays broke the molecules apart. Much of the freed hydrogen escaped into space, and Venus lost its water. Without water, Venus became less and less like Earth and kept an atmosphere filled with carbon dioxide. The carbon dioxide acts as a blanket, creating an intense greenhouse effect and driving surface temperatures high enough to melt lead and to prohibit the formation of carbonate minerals. Volcanoes continually vented more carbon dioxide into the atmosphere. On Earth, liquid water removes carbon dioxide from the atmosphere and combines it with calcium, from rock weathering, to form carbonate sedimentary rocks. Without liquid water to remove carbon from the atmosphere, the level of carbon dioxide in the atmosphere of Venus remains high. Like Venus, Earth is large enough to be geologically active and for its gravitational field to hold an atmosphere. Unlike Venus, it is just the right distance from the Sun so that temperature ranges allow water to exist as a liquid, a solid, and a gas. Water is thus extremely mobile and moves rapidly over the planet in a continuous hydrologic cycle. Heated by the Sun, the water moves in great cycles from the oceans to the atmosphere, over the landscape in river systems, and ultimately back to the oceans. As a result, Earth's surface has been continually changed and eroded into delicate systems of river valleys, a remarkable contrast to the surfaces of other planetary bodies where impact craters dominate. Few areas on Earth have been untouched by flowing water. As a result, river valleys are the dominant feature of its landscape. Similarly, wind action has scoured fine particles away from large areas, depositing them elsewhere as vast sand seas dominated by dunes or in sheets of loess. These fluid movements are caused by gravity flow systems energized by heat from the Sun. Other geologic changes occur when the gases in the atmosphere or water react with rocks at the surface to form new chemical compounds with different properties. An important example of this process was the removal of most of Earth's carbon dioxide from its atmosphere to form carbonate rocks. However, if Earth were a little closer to the Sun, its oceans would evaporate. If it were farther from the Sun, the oceans would freeze solid. Because liquid water was present, self-replicating molecules of carbon, hydrogen, and oxygen developed life early in Earth's history and have radically modified its surface, blanketing huge parts of the continents with greenery. Life thrives on this planet, and it helped create the planet's oxygen and nitrogen-rich atmosphere and moderate temperatures. 50 to 3-star death. Until the early to mid-20th century, scientists believed that stars generate energy by shrinking. As stars contracted, it was thought they would get hotter and hotter, giving off light in the process. This could not be the primary way that stars shine, however. If it were, they would scarcely last a million years, rather than the billions of years in age that we know they are. We now know that stars are fueled by nuclear fusion. Each time fusion takes place, energy is released as a byproduct. This energy, expelled into space, is what we see as starlight. The fusion process begins when two hydrogen nuclei smash together to form a particle called the deuteron. Deuterons readily combine with additional protons to form helium. Helium, in turn, can fuse together to form heavier elements such as carbon. In a typical star, merger after merger takes place until significant quantities of heavy elements are built up. We must distinguish, at this point, between two different stellar types, population 1 and population LL, the latter being much older than the former. These groups can also be distinguished by their locations. Our galaxy, the Milky Way, is shaped like a flat disk surrounding a central bulge. Whereas population 1 stars are found mainly in the galactic disk, population 2 stars mostly reside in the central bulge of the galaxy and in the halo surrounding this bulge. Population 2 stars date to the early stages of the universe. Formed when the cosmos was filled with hydrogen and helium gases, they initially contained virtually no heavy elements. They shine until their fusible material is exhausted. When population 2 stars die, their material is spread out into space. Some of this dust is eventually incorporated into newly formed population 1 stars. Though population 1 stars consist mostly of hydrogen and helium gas, they also contain heavy elements, which comprise about 1 or 2% of their mass. These heavier materials are fused from the lighter elements that the stars have collected. Thus, population 1 stars contain material that once belonged to stars from previous generations. The Sun is a good example of a population 1 star. What will happen when the Sun dies? In several billion years, our mother star will burn much brighter. It will expend more and more of its nuclear fuel, until little is left of its original hydrogen. Then, at some point in the far future, all nuclear reactions in the Sun's center will cease. Once the Sun passes into its post-nuclear phase, it will separate effectively into two different regions, an inner zone and an outer zone. While no more hydrogen fuel will remain in the inner zone, there will be a small amount left in the outer zone. Rapidly, changes will begin to take place that will serve to tear the Sun apart. The inner zone, its nuclear fires no longer burning, will begin to collapse under the influence of its own weight and will contract into a tiny hot core, dense and dim. An opposite fate will await the outer region, a loosely held together ball of gas. A shock wave caused by the inner zone's contraction will send ripples through the dying star, pushing the stellar exterior's material farther and farther outward. The outer envelope will then grow rapidly, increasing, in a short interval, hundreds of times in size. As it expands, it will cool down by thousands of degrees. Eventually, the Sun will become a red giant star, cool and bright. It will be so large that it will occupy the whole space that used to be the Earth's orbit and so brilliant that it would be able to be seen with the naked eye thousands of light years away. It will exist that way for millions of years, gradually releasing the material of its outer envelope into space. Finally, nothing will be left of the gaseous exterior of the Sun, all that will remain will be the hot, white core. The Sun will have become a white dwarf star. The core will shrink, giving off the last of its energy, and the Sun will finally die. 42-3 Callisto and Ganymede. From 1996 to 1999, the Galileo spacecraft passed through the Jovian system, providing much information about Jupiter's satellites. Callisto, the outermost of Jupiter's four largest satellites, orbits the planet in 17 days at a distance from Jupiter of 2 million kilometers. Like our own moon, Callisto rotates in the same period as it revolves, so it always keeps the same face toward Jupiter. Its noontime surface temperature is only about -140 degrees Celsius, so water ice is stable on its surface year-round. Callisto has a diameter of 4.820 kilometers, almost the same as that of Mercury. Its mass is only one-third as great, which means its density must be only one-third as great as well. This tells us that Callisto has far less of the rocky metallic materials found in the inner planets and must instead be an icy body through much of its interior. Callisto has not fully differentiated, meaning separated into layers of different density materials. Astronomers can tell that it lacks a dense core from the details of its gravitational pull on the Galileo spacecraft during several very close flybys. This fact surprised scientists, who expected that all the big icy moons would be differentiated. It is much easier for an icy body to differentiate than for a rocky one, since the melting temperature of ice is so low. Only a little heating will soften the ice and get the process started, allowing the rock and metal to sink to the center and the slushy ice to float to the surface. Yet Callisto seems to have frozen solid before the process of differentiation was complete. Like our moon's Highlands, the surface of Callisto is covered with impact craters. The survival of these craters tells us that an icy object can form and retain impact craters in its surface. In thinking of ice so far from the sun, it is important not to judge its behavior from that of the much warmer ice we know on Earth. At the temperatures of the outer solar system, ice on the surface is nearly as hard as rock, and behaves similarly. Ice on Callisto does not deform or flow like ice in glaciers on Earth. Callisto is unique among the planet-sized objects of the solar system in its absence of interior forces to drive geological evolution. The satellite was born dead and has remained geologically dead for more than 4 billion years. Ganymede, another of Jupiter's satellites and the largest in our solar system, is also cratered, but less so than Callisto. About 1/4 of its surface seems to be as old and heavily cratered, the rest formed more recently, as we can tell by the sparse covering of impact craters as well as the relative freshness of the craters. Ganymede is a differentiated world, like the terrestrial planets. Measurements of its gravity field tell us that the rock and metal sank to form a core about the size of our moon, with a mantle and crust of ice floating above it. In addition, the Galileo spacecraft discovered that Ganymede has a magnetic field, the signature of a partially molten interior. Ganymede is not a dead world, but rather a place of continuing geological activity powered by an internal heat source. Much of its surface may be as young as 500 million years. The younger terrain is the result of tectonic and volcanic forces. Some features formed when the crust cracked, flooding many of the craters with water from the interior. Extensive mountain ranges were formed from compression of the crust, forming long ridges with parallel valleys spaced 1 to 2 kilometers apart. In some places, older impact craters were split and pulled apart. There are even indications of large-scale crustal movements that are similar to the plate tectonics of Earth. Why is Ganymede different from Callisto? Possibly the small difference in size and internal heating between the two led to this divergence in their evolution. But more likely, the gravity of Jupiter is to blame for Ganymede's continuing geological activity. Ganymede is close enough to Jupiter that tidal forces from the giant planet may have episodically heated its interior and triggered major convulsions on its crust. 41:2 Climate of Venus. Earth has abundant water in its oceans but very little carbon dioxide in its relatively thin atmosphere. By contrast, Venus is very dry and its thick atmosphere is mostly carbon dioxide. The original atmospheres of both Venus and Earth were derived at least in part from gases spewed forth, or outgassed, by volcanoes. The gases that emanate from present-day volcanoes on Earth, such as Mount St. Helens, are predominantly water vapor, carbon dioxide, and sulfur dioxide. These gases should therefore have been important parts of the original atmospheres of both Venus and Earth. Much of the water on both planets is also thought to have come from impacts from comets, icy bodies formed in the outer solar system. In fact, water probably once dominated the Venusian atmosphere. Venus and Earth are similar in size and mass, so Venusian volcanoes may well have outgassed as much water vapor as on Earth, and both planets would have had about the same number of comets strike their surfaces. Studies of how stars evolved suggest that the early Sun was only about 70% as luminous as it is now, so the temperature in Venus' early atmosphere must have been quite a bit lower. Thus water vapor would have been able to liquefy and form oceans on Venus. But if water vapor and carbon dioxide were once so common in the atmospheres of both Earth and Venus, what became of Earth's carbon dioxide? And what happened to the water on Venus? The answer to the first question is that carbon dioxide is still found in abundance on Earth, but now, instead of being in the form of atmospheric carbon dioxide, it is either dissolved in the oceans or chemically bound into carbonate rocks, such as the limestone and marble that formed in the oceans. If Earth became as hot as Venus, much of its carbon dioxide would be boiled out of the oceans and baked out of the crust. Our planet would soon develop a thick, oppressive carbon dioxide atmosphere much like that of Venus. To answer the question about Venus' lack of water, we must return to the early history of the planet. Just as on present-day Earth, the oceans of Venus limited the amount of atmospheric carbon dioxide by dissolving it in the oceans and binding it up in carbonate rocks. But being closer to the Sun than Earth is, enough of the liquid water on Venus would have vaporized to create a thick cover of water vapor clouds. Since water vapor is a greenhouse gas, this humid atmosphere, perhaps denser than Earth's present-day atmosphere, but far less dense than the atmosphere that envelopes Venus today, would have efficiently trapped heat from the Sun. At first, this would have had little effect on the oceans of Venus. Although the temperature would have climbed above 100 degrees Celsius, the boiling point of water at sea level on Earth, the added atmospheric pressure from water vapor would have kept the water in Venus oceans in the liquid state. This hot and humid state of affairs may have persisted for several hundred million years. But as the Sun's energy output slowly increased over time, the temperature at the surface would eventually have risen above 374 degrees Celsius. Above this temperature, no matter what the atmospheric pressure, Venus oceans would have begun to evaporate, and the added water vapor in the atmosphere would have increased the greenhouse effect. This would have made the temperature even higher and caused the oceans to evaporate faster, producing more water vapor. That, in turn, would have further intensified the greenhouse effect and made the temperature climb higher still. Once Venus oceans disappeared, so did the mechanism for removing carbon dioxide from the atmosphere. With no oceans to dissolve it, outgassed carbon dioxide began to accumulate in the atmosphere, intensifying the greenhouse effect even more. Temperatures eventually became high enough to bake out any carbon dioxide that was trapped in carbonate rocks. This liberated carbon dioxide formed the thick atmosphere of present-day Venus. Over time, the rising temperatures would have leveled off, solar ultraviolet radiation having broken down atmospheric water vapor molecules into hydrogen and oxygen. With all the water vapor gone, the greenhouse effect would no longer have accelerated. 53-1 Evidence of the earliest writing. Although literacy appeared independently in several parts of the prehistoric world, the earliest evidence of writing is the cuneiform Sumerian script on the clay tablets of ancient Mesopotamia, which, archaeological detective work has revealed, had its origins in the accounting practices of commercial activity. Researchers demonstrated that preliterate people, to keep track of the goods they produced and exchanged, created a system of accounting using clay tokens as symbolic representations of their products. Over many thousands of years, the symbols evolved through several stages of abstraction until they became wedge-shaped. Signs on clay tablets, recognizable as writing. The original tokens were three-dimensional solid shapes, tiny spheres, cones, discs, and cylinders. A debt of 6 units of grain and 8 head of livestock, for example, might have been represented by 6 conical and 8 cylindrical tokens. To keep batches of tokens together, an innovation was introduced, whereby they were sealed inside clay envelopes that could be broken open and counted when it came time for a debt to be repaid. But because the contents of the envelopes could easily be forgotten, two-dimensional representations of the three-dimensional tokens were impressed into the surface of the envelopes before they were sealed. Eventually, having 2 sets of equivalent symbols, the internal tokens and external markings, came to seem redundant, so the tokens were eliminated, and only solid clay tablets with two-dimensional symbols were retained. Over time, the symbols became more numerous, varied, and abstract and came to represent more than trade commodities, evolving eventually into cuneiform writing. The evolution of the symbolism is reflected in the archaeological record first of all by the increasing complexity of the tokens themselves. The earliest tokens, dating from about 10,000 to 6,000 years ago, were of only the simplest geometric shapes. But about 3,500 BCE, more complex tokens came into common usage, including many naturalistic forms shaped like miniature tools, furniture, fruit, and humans. The earlier, plain tokens were counters for agricultural products, whereas the complex ones stood for finished products, such as bread, oil, perfume, wool, and rope, and for items produced in workshops, such as metal, bracelets, types of cloth, garments, mats, pieces of furniture, tools, and a variety of stone and pottery vessels. The signs marked on clay tablets likewise evolved from simple wedges, circles, ovals, and triangles based on the plane tokens to pictographs derived from the complex tokens. Before this evidence came to light, the inventors of writing were assumed by researchers to have been an intellectual elite. Some, for example, hypothesized that writing emerged when members of the priestly caste agreed among themselves on written signs. But the association of the plane tokens with the first farmers and of the complex tokens with the first artisans, and the fact that the token and envelope accounting system invariably represented only small-scale transactions, testifies to the relatively modest social status of the creators of writing. And not only of literacy, but numeracy as well. The evidence of the tokens provides further confirmation that mathematics originated in people's desire to keep records of flocks and other goods. Another immensely significant step occurred around 3100 BCE, when Sumerian accountants extended the token-based signs to include the first real numerals. Previously, units of grain had been represented by direct one-to-one correspondence, by repeating the token or symbol for a unit of grain the required number of times. The accountants, however, devised numeral signs distinct from commodity signs, so that 18 units of grain could be indicated by preceding a single grain symbol with a symbol denoting 18. Their invention of abstract numerals and abstract counting was one of the most revolutionary advances in the history of mathematics. What was the social status of the anonymous accountants who produced this breakthrough? The immense volume of clay tablets unearthed in the ruins of the Sumerian temples where the accounts were kept suggests a social differentiation within the scribal class. With a virtual army of lower-ranking tabulators performing the monotonous job of tallying commodities. We can only speculate as to how high or low the inventors of true numerals were in the scribal hierarchy, but it stands to reason that this labor-saving innovation would have been the brainchild of the lower-ranking types whose drudgery is eased. 53-3 Paleolithic Cave Paintings. In any investigation of the origins of art, attention focuses on the cave paintings created in Europe during the Paleolithic era, such as those depicting bulls and other animals in the Lascaux cave in France. Accepting that they are the best preserved and most visible signs of what was a global creative explosion, how do we start to explain their appearance? Instinctively, we may want to update the earliest human artists by assuming that they painted for the sheer joy of painting. The philosophers of classical Greece recognized it as a defining trait of humans to delight in works of imitation, to enjoy the very act and triumph of representation. If we were close to a real lion or snake, we might feel frightened. But a well-executed picture of a lion or snake will give us pleasure. Why suppose that our Paleolithic ancestors were any different? This simple acceptance of art for art's sake has a certain appeal. To think of Lascaux as a gallery allows it to be a sort of special viewing place where the handiwork of accomplished artists might be displayed. Plausibly, daily existence in parts of Paleolithic Europe may not have been so hard, with an abundance of ready food and therefore the leisure time for art. The problems with this explanation, however, are various. In the first place, the proliferation of archaeological discoveries, and this includes some of the world's innumerable rock art sites that cannot be dated, has served to emphasize a remarkably limited repertoire of subjects. The images that recur are those of animals. Human figures are unusual, and when they do make an appearance, they are rarely done with the same attention to form accorded to the animals. If Paleolithic artists were simply seeking to represent the beauty of the world around them, would they not have left a far greater range of pictures, of trees, flowers, of the sun and the stars? A further question to the theory of art for art's sake is posed by the high incidence of Paleolithic images that appear not to be imitative of any reality whatsoever. These are geometrical shapes or patterns consisting of dots or lines. Such marks may be found isolated or repeated over a particular surface, but also scattered across more recognizable forms. A good example of this may be seen in the geologically spectacular grotto of Péchimerle, in the Lot region of France. Here we encounter some favorite animals from the Paleolithic repertoire, a pair of stop-bellied horses. But over and around the horses' outlines are multiple dark spots, daubed in disregard for the otherwise naturalistic representation of animals. What does such patterning imitate? There is also the factor of location. The caves of Lascaux might conceivably qualify as underground galleries, but many other paintings have been found in recesses totally unsuitable for any kind of viewing, tight nooks and crannies that must have been awkward even for the artists to penetrate, let alone for anyone else wanting to see the art. Finally, we may doubt the notion that the Upper Paleolithic period was a paradise in which food came readily, leaving humans ample time to amuse themselves with art. For Europe, it was still the Ice Age. An estimate of the basic level of sustenance then necessary for human survival has been judged at 2,200 calories per day. This consideration, combined with the stark emphasis upon animals in the cave art, has persuaded some archaeologists that the primary motive behind Paleolithic images must lie with the primary activity of Paleolithic people, hunting. Hunting is a skill. Tracking, stalking, chasing, and killing the prey are difficult, sometimes dangerous activities. What if the process could be made easier by art? In the early decades of the 20th century, Abbé Henri Breuil argued that the cave paintings were all about sympathetic magic. The artists strived diligently to make their animal images evocative and realistic because they were attempting to capture the spirit of their prey. What could have prompted their studious attention to making such naturalistic, recognizable images? According to Breuil, the artists may have believed that if a hunter were able to make a true likeness of some animal, then that animal was virtually trapped. Images, therefore, may have had the magical capacity to confer success or luck in the hunt. 52-2 Natufian culture. In the archaeological record of the Natufian period, from about 12,500 to 10,200 years ago, in the part of the Middle East known as the Levant roughly east of the Mediterranean and north of the Arabian Peninsula, we see clear evidence of agricultural origins. The stone tools of the Natufians included many sickle-shaped cutting blades that show a pattern of wear characteristic of cereal harvesting. Also, querns and other stone tools used for processing grain occur in abundance at Natufian sites, and many such tools show signs of long, intensive use. Along with the sickle blades are many grinding stones, primarily mortars and pestles of limestone or basalt. There is also evidence that these heavy grinding stones were transported over long distances, more than 30 kilometers in some cases, and this is not something known to have been done by people of preceding periods. Fishhooks and weights for sinking fishing nets attest to the growing importance of fish in the diet in some areas. Stone vessels indicate an increased need for containers, but there is no evidence of Natufian clay working or pottery. Studies of the teeth of Natufians also strongly suggest that these people specialized in collecting cereals and may have been cultivating them and in the process of domesticating them, but they were also still hunter-foragers who intensively hunted gazelle and deer in more lush areas and wild goats and equids in more arid zones. The Natufians had a different settlement pattern from that of their predecessors. Some of their base camps were far larger than any of those belonging to earlier periods, and they may have lived in some of these camps for half the year or even more. In some of the camps, people made foundations and other architectural elements out of limestone blocks. Trade in shell, obsidian, and other commodities seems to have been on the rise, and anthropologists suspect that the exchange of perishables and salt was also on the increase. With the growing importance of wild cereals in the diet, salt probably became for the first time a near necessity. People who eat a lot of meat get many essential salts from this diet, but diets based on cereals can be deficient in salts. Salt was probably also important as a food preservative in early villages. As always, there is more to a major cultural change than simply a shift in economics. The Natufians made beads and pendants in many materials, including gemstones and marine shells that had to be imported, and it is possible that this ornamentation actually reflects a growing sense of ethnic identity and perhaps some differences in personal and group status. Cleverly carved figurines of animals, women, and other subjects occur in many sites, and Natufian period cave paintings have been found in Anatolia, Syria, and Iran. More than 400 Natufian burials have been found, most of them simple graves set in house floors. As archaeologist Belfer Cohen notes, these burials may reflect an ancestor cult and a growing sense of community emotional ties and attachment to a particular place, and toward the end of the Natufian period, people in this area were making a strict separation between living quarters and burial grounds. In contrast with the Pleistocene cultures of the Levant, Natufian culture appears to have experienced considerable social change. The question of why the Natufians differed from their predecessors in these and other ways and why they made these first steps toward farming as a way of life remains unclear. There were climate changes, of course, and growing aridity and rising population densities may have forced them to intensify the exploitation of cereals, which in turn might have stimulated the development of sickles and other tools and the permanent communities that make agriculture efficient. But precisely how these factors interacted with others at play is poorly understood. 52-3 Early food production in Sub-Saharan Africa. At the end of the Pleistocene, the technologies of food production may have already been employed on the fringes of the rainforests of Western and Central Africa, where the common use of such root plants as the African yam led people to recognize the advantages of growing their own food. The yam can easily be resprouted if the top is replanted. This primitive form of viticulture may have been the economic tradition onto which the cultivation of summer rainfall cereal crops was grafted as it came into use south of the grassland areas on the Sahara's southern borders. As the Sahara dried up after 1500 BC, pastoral peoples moved southward along major watercourses into the savanna belt of West Africa and the Sudan. By 3000 BC, just as ancient Egyptian civilization was coming into being along the Nile, they had settled in the heart of the East African highlands far to the south. The East African highlands are ideal cattle country and the home today of such famous cattle herding peoples as the Maasai. The highlands were inhabited by hunter-gatherers living around mountains near the plains until about 3300 BC, when the first cattle herders appeared. These cattle people may have moved between fixed settlements during the wet and dry seasons, living off hunting in the dry months and their own livestock and agriculture during the rains. As was the case elsewhere, cattle were demanding animals in Africa. They required water at least every 24 hours and large tracts of grazing grass if herds of any size were to be maintained. The secret was the careful selection of grazing land, especially in environments where seasonal rainfall led to marked differences in graze quality throughout the year. Even modest cattle herds required plenty of land and considerable mobility. To acquire such land often required moving herds considerable distances, even from summer to winter pastures. At the same time, the cattle owners had to graze their stock in tsetse fly-free areas. The only protection against human and animal sleeping sickness, a disease carried by the tsetse fly, was to avoid settling or farming such areas. A constraint severely limiting the movements of cattle-owning farmers in eastern and central Africa. As a result, small cattle herds spread south rapidly in areas where they could be grazed long before cereal agriculture took hold far south of the Sahara. Some hunter-gatherer groups in the savanna woodlands of eastern and southern Africa may have acquired cattle, and perhaps other domesticated animals, by gift exchange or through raids on herding neighbors. Contrary to popular belief, there is no such phenomenon as pure pastoralists, a society that subsists on its herds alone. The Saharan herders who moved southward to escape drought were almost certainly also cultivating sorghum, millet, and other tropical rainfall crops. By 1500 BC, cereal agriculture was widespread throughout the savanna belt south of the Sahara. Small farming communities dotted the grasslands and forest margins of eastern West Africa, all of them depending on what is called shifting agriculture. This form of agriculture involved clearing woodland, burning the felled brush over the cleared plot, mixing the ash into the soil, and then cultivating the prepared fields. After a few years, the soil was exhausted, so the farmer moved on, exploiting new woodland and leaving the abandoned fields to lie fallow. Shifting agriculture, often called slash-and-burn, was highly adaptive for savanna farmers without plows, for it allowed cereal farming with the minimal expenditure of energy. The process of clearance and burning may have seemed haphazard to the uninformed eye, but it was not. Except in favored areas, such as regularly inundated floodplains, tropical Africas. Soils were of only moderate to low fertility. The art of farming was careful soil selection, that is, knowing which soils were light and easily cultivable, could be readily turned with small hoes, and would maintain their fertility over several years. Planting, for cereal crops rapidly remove nitrogen and other nutrients from the soil. Once it had taken hold, slash-and-burn agriculture expanded its frontiers rapidly as village after village took up new lands, moving forward so rapidly that one expert has estimated it took a mere 2 centuries to cover 2,000 kilometers from eastern to southern Africa. 51-1 Memphis, United Egypt's first capital. The city of Memphis, located on the Nile near the modern city of Cairo, was founded around 3100 BC as the first capital of a recently united Egypt. The choice of Memphis by Egypt's first kings reflects the site's strategic importance. First, and most obvious, the apex of the Nile River Delta was a politically opportune location for the state's administrative center, standing between the united lands of Upper and Lower Egypt and offering ready access to both parts of the country. The older pre-dynastic centers of power, this and Hierakonpolis, were too remote from the vast expanse of the delta, which had been incorporated into the unified state. Only a city within easy reach of both the Nile Valley to the south and the more spread out, difficult terrain to the north could provide the necessary political control that the rulers of early dynastic Egypt required. The region of Memphis must have also served as an important node for transport and communications, even before the unification of Egypt. The region probably acted as a conduit for much, if not all, of the river-based trade between northern and southern Egypt. Moreover, commodities imported from the Near East by the royal courts of pre-dynastic Upper Egypt would have been channeled through the Memphis region on their way south. In short, therefore, the site of Memphis offered the rulers of the early dynastic period an ideal location for controlling internal trade within their realm, an essential requirement for a state-directed economy that depended on the movement of goods. Equally important for the national administration was the ability to control communications within Egypt. The Nile provided the easiest and quickest artery of communication, and the national capital was, again, ideally located in this respect. Recent geological surveys of the Memphis region have revealed much about its topography in ancient times. It appears that the location of Memphis may have been even more advantageous for controlling trade, transport, and communications than was previously appreciated. Surveys and drill cores have shown that the level of the Nile floodplain has steadily risen over the last 5 millenniums. When the floodplain was much lower, as it would have been in pre-dynastic and early dynastic times, the outwash fans of various wadis would have been much more prominent features on the east bank. The fan associated with the Wadi Hof extended a significant way into the Nile floodplain, forming a constriction in the vicinity of Memphis. The valley may have narrowed at this point to a mere 3 kilometers, making it the ideal place for controlling river traffic. Furthermore, the Memphis region seems to have been favorably located for the control not only of river-based trade but also of desert trade routes. The 2 outwash fans in the area gave access to the extensive wadi systems of the eastern desert. In pre-dynastic times, the Wadi Diglab may have served as a trade route between the Memphis region and the Near East, to judge from the unusual concentration of foreign artifacts found in the pre-dynastic settlement of Madi. Access to, and control of, trade routes between Egypt and the Near East seems to have been a preoccupation of Egypt's rulers during the period of state formation. The desire to monopolize foreign trade may have been one of the primary factors behind the political unification of Egypt. The foundation of the national capital at the junction of an important trade route with the Nile Valley is not likely to have been accidental. Moreover, the Wadis Hof and Digla provided the Memphis region with accessible desert pasturage. As was the case with the cities of Hierakonpolis and El-Kab, the combination within the same area of both desert pasturage and alluvial arable land was a particularly attractive one for early settlement. This combination no doubt contributed to the prosperity of the Memphis region from early pre-dynastic times. 51-3 population growth in 19th century Europe because of industrialization, but also because of a vast increase in agricultural output without which industrialization would have been impossible. Western Europeans by the latter half of the 19th century enjoyed higher standards of living and longer, healthier lives than most of the world's peoples. In Europe as a whole, the population rose from 188 million in 1800 to 400 million in 1900. By 1900, virtually every area of Europe had contributed to the tremendous surge of population, but each major region was at a different stage of demographic change. Improvements in the food supply continued trends that had started in the late 17th century. New lands were put under cultivation, while the use of crops of American origin, particularly the potato, continued to expand. Setbacks did occur. Regional agricultural failures were the most common cause of economic recessions until 1850, and they could lead to localized famine as well. A major potato blight in 1846 to 1847 led to the deaths of at least 1 million persons in Ireland and the emigration of another million, and Ireland never recovered the population levels the potato had sustained to that point. Bad grain harvests at the same time led to increased hardship throughout much of Europe. After 1850, however, the expansion of foods more regularly kept pace with population growth, though the poorer classes remained malnourished. Two developments were crucial. First, the application of science and new technology to agriculture increased. Led by German universities, increasing research was devoted to improving seeds, developing chemical fertilizers, and advancing livestock. After 1861, with the development of land-grant universities in the United States that had huge agricultural programs, American crop production research added to this mix. Mechanization included the use of horse-drawn harvesters and seed drills, many developed initially in the United States. It also included mechanical cream separators and other food processing devices that improved supply. The second development involved industrially based transportation. With trains and steam shipping, it became possible to move foods to needy regions within Western Europe quickly. Famine became a thing of the past. Many Western European countries, headed by Britain, began also to import increasing amounts of food, not only from Eastern Europe, a traditional source, but also from the Americas, Australia, and New Zealand. Steam shipping, which improved speed and capacity, as well as new procedures for canning and refrigerating foods, was fundamental to these developments. Europe's population growth included one additional innovation by the 19th century: it combined with rapid urbanization. More and more Western Europeans moved from countryside to city, and big cities grew most rapidly of all. By 1850, over half of all the people in England lived in cities, a first in human history. In one sense, this pattern seems inevitable: growing numbers of people pressed available resources on the land, even when farm work was combined with a bit of manufacturing, so people crowded into cities seeking work or other resources. Traditionally, however, death rates in cities surpassed those in the countryside by a large margin. Cities had maintained population only through steady immigration. Thus, rapid urbanization should have reduced overall population growth, but by the middle of the 19th century this was no longer the case. Urban death rates remained high, particularly in the lower-class slums, but they began to decline rapidly. The greater reliability of food supplies was a factor in the decline of urban death rates. Even more important were the gains in urban sanitation, as well as measures such as inspection of housing. Reformers, including enlightened doctors, began to study the causes of high death rates and to urge remediation. Even before the discovery of germs, beliefs that disease spread by miasmas prompted attention to sewers and open garbage. Edwin Chadwick led an exemplary urban crusade for underground sewers in England in the 1830s. Gradually, public health provisions began to cut into customary urban mortality rates. By 1900, in some parts of Western Europe, life expectancy in the cities began to surpass that of the rural areas. Industrial societies had figured out ways to combine large and growing cities with population growth, a development that would soon spread to other parts of the world. 50-to-1 American railroads. In the United States, railroads spearheaded the second phase of the transportation revolution by overtaking the previous importance of canals. The mid-1800s saw great expansion of American railroads. The major cities east of the Mississippi River were linked by a spiderweb of railroad tracks. Chicago's growth illustrates the impact of these rail links. In 1849, Chicago was a village of a few hundred people with virtually no rail service. By 1860, it had become a city of 100,000, served by 11 railroads. Farmers to the north and west of Chicago no longer had to ship their grain, livestock, and dairy products down the Mississippi River to New Orleans. They could now ship their products directly east. Chicago supplanted New Orleans as the interior of America's main commercial hub. The east-west rail lines stimulated the settlement and agricultural development of the Midwest. By 1860, Illinois, Indiana, and Wisconsin had replaced Ohio, Pennsylvania, and New York as the leading wheat-growing states. Enabling farmers to speed their products to the east, railroads increased the value of farmland and promoted additional settlement. In turn, population growth in agricultural areas triggered industrial development in cities such as Chicago, Davenport, and Minneapolis, for the new settlers needed lumber for fences and houses and mills to grind wheat into flour. Railroads also propelled the growth of small towns along their routes. The Illinois Central Railroad, which had more track than any other railroad in 1855, made money not only from its traffic but also from real estate speculation. Purchasing land for stations along its path, the Illinois Central then laid out towns around the stations. The selection of Montino, Illinois, as a stop of the Illinois Central, for example, transformed the site from a crossroads without a single house in 1854 into a bustling town of nearly 1,000 in 1860, replete with hotels, lumberyards, grain elevators, and grist mills. By the Civil War, few thought of the railroad-linked Midwest as a frontier region or viewed its inhabitants as pioneers. As the nation's first big business, the railroads transformed the conduct of business. During the early 1830s, railroads, like canals, depended on financial aid from state governments. With the onset of economic depression in the late 1830s, however, state governments scrapped overly ambitious railroad projects. Convinced that railroads burdened them with high taxes and blasted hopes, voters turned against state aid, and in the early 1840s, several states amended their constitutions to bar state funding for railroads and canals. The federal government took up some of the slack, but federal aid did not provide a major stimulus to railroads before 1860. Rather, part of the burden of finance passed to city and county governments in agricultural areas that wanted to attract railroads. Such municipal governments, for example, often gave railroads rights-of-way, grants of land for stations, and public funds. The dramatic expansion of the railroad network in the 1850s, however, strained the financing capacity of local governments and required a turn toward private investment, which had never been absent from the picture. Well aware of the economic benefits of railroads, individuals living near them had long purchased railroad stock issued by governments and had directly bought stock in railroads, often paying by contributing their labor to building the railroads. But the large railroads of the 1850s needed more capital than such small investors could generate. Gradually, the center of railroad financing shifted to New York City, and in fact, it was the railroad boom of the 1850s that helped make Wall Street in New York City the nation's greatest capital market. The stocks of all the leading railroads were traded on the floor of the New York Stock Exchange during the 1850s. In addition, the growth of railroads turned New York City into the center of modern investment firms. The investment firms evaluated the stock of railroads in the smaller American cities and then found purchasers for these stocks in New York City, Philadelphia, Paris, London, Amsterdam, and Hamburg. Controlling the flow of funds to railroads, the investment bankers began to exert influence over the railroad's internal affairs by supervising administrative reorganizations in times of trouble. 50-2 The achievement of Brazilian independence in contrast to the political anarchy, economic dislocation, and military destruction in Spanish America, Brazil's drive toward independence from Portugal proceeded as a relatively bloodless transition between 1808 and 1822. The idea of Brazilian independence first arose in the late 18th century as a Brazilian reaction to the Portuguese policy of tightening political and economic control over the colony in the interests of the mother country. The first significant conspiracy against Portuguese rule was organized from 1788 to 1799 in the province of Minas Gerais, where rigid governmental control over the production and prices of gold and diamonds, as well as heavy taxes, caused much discontent. But this conspiracy never went beyond the stage of discussion and was easily discovered and crushed. Other conspiracies in the late 18th century, as well as a brief revolt in 1817, reflected the influence of Republican ideas over sections of the elite and even the lower strata of urban society. All proved abortive or were soon crushed. Were it not for an accident of European history, the independence of Brazil might have been long delayed. The French invasion of Portugal in 1807, followed by the flight of the Portuguese court to Rio de Janeiro, brought large benefits to Brazil. Indeed, the transfer of the court in effect signified achievement of Brazilian independence. The Portuguese prince and future King João VI opened Brazil's ports to the trade of friendly nations, permitted the rise of local industries, and founded the Bank of Brazil. In 1815 he elevated Brazil to the legal status of a kingdom co-equal with Portugal. In one sense, however, Brazil's new status signified the substitution of one dependence for another. Freed from Portuguese control, Brazil came under the economic dominance of England, which obtained major tariff concessions and other privileges by the Strangford Treaty of 1810 between Portugal and Great Britain. The treaty provided for the importation of British manufactures into Brazil and the export of Brazilian agricultural produce to Great Britain. One result was an influx of cheap machine-made goods that swamped the handicrafts industry of the country. Brazilian elites took satisfaction in Brazil's new role and the growth of educational, cultural, and economic opportunities for their class. But the feeling was mixed with resentment toward the thousands of Portuguese courtiers and hangers-on who came with the court and who competed with Brazilians for jobs and favors. Thus, the change in the status of Brazil sharpened the conflict between Portuguese elites born in Brazil and elites born in Portugal and loyal to the Portuguese crown. The event that precipitated the break with the mother country was the Revolution of 1820 in Portugal. The Portuguese revolutionaries framed a liberal constitution for the kingdom, but they were conservative or reactionary in relation to Brazil. They demanded the immediate return of King João to Lisbon, an end to the system of dual monarchy that he had devised, and the restoration of the Portuguese commercial monopoly. Timid and vacillating, King João did not know which way to turn. Under the pressure of his courtiers, who hungered to return to Portugal and their lost estates, he finally approved the new constitution and sailed for Portugal. He left behind him, however, his son and heir, Pedro, and in a private letter advised him that in the event the Brazilians should demand independence, he should assume leadership of the movement and set the crown of Brazil on his head. Soon it became clear that the Portuguese parliament intended to set the clock back by abrogating all the liberties and concessions won by Brazil since 1808. One of its decrees insisted on the immediate return of Pedro from Brazil. The pace of events moved more rapidly in 1822. On January 9, urged on by Brazilian advisers who perceived a golden opportunity to make an orderly transition to independence without the intervention of the masses, Pedro refused an order from the parliament to return to Portugal, saying famously, "I'll remain." On September 7, regarded by all Brazilians as Independence Day, he issued the even more celebrated proclamation, "Independence or Death." In December 1822, having overcome slight resistance by Portuguese troops, Dom Pedro was formally proclaimed constitutional emperor of Brazil. 49-2 Moveable Type. Nothing divided the medieval world in Europe more decisively from the early modern period than printing with movable type. It was a German invention and the culmination of a complex process. The world of antiquity had recorded its writings mainly on papyrus. Between 200 BC and AD 300, this was supplemented by vellum, calf skin treated and then smoothed by pumice stone. To this in late Roman times was added parchment, similarly made from the smooth skin of sheep or goats. In the early Middle Ages, Europe imported an industrial process from China, which turned almost any kind of fibrous material into pulp that was then spread in sheets. This was known as cloth parchment. By about 1150, the Spanish had developed the first mill for making cheap paper, a word contracted from papyrus, which became the standard term. One of the most important phenomena of the later Middle Ages was the growing availability of cheap paper. Even in England, where technology lagged far behind, a sheet of paper, or 8 octavo pages, cost only a penny by the 15th century. In the years 1446 to 1448, two German goldsmiths, Johannes Gutenberg and Johann Fust, made use of cheap paper to introduce a critical improvement in the way written pages were reproduced. Printing from wooden blocks was the old method. What the Germans did was to invent movable type for the letterpress. It had 3 merits: it could be used repeatedly until worn out, it was cast in metal from a mold and so could be renewed without difficulty, and it made lettering uniform. In 1450, Gutenberg began work on his Bible, the first printed book, known as the Gutenberg. It was completed in 1455 and is a marvel. As Gutenberg, apart from getting the key idea, had to solve a lot of practical problems, including imposing paper and ink into the process and the actual printing itself, for which he adapted the screw press used by winemakers. It is amazing that his first product does not look at all rudimentary. Those who handle it are struck by its clarity and quality. Printing was one of those technical revolutions that developed its own momentum at extraordinary speed. Europe in the 15th century was a place where intermediate technology, that is, workshops with skilled craftspeople, was well established and spreading fast, especially in Germany and Italy. Such workshops were able to take on printing easily, and it thus became Europe's first true industry. The process was aided by two factors: the new demand for cheap classical texts and the translation of the Latin Bible into modern languages. Works of reference were also in demand. Presses sprang up in several German cities, and by 1470, Nuremberg, Germany had established itself as the center of the international publishing trade, printing books from 24 presses and distributing them at trade fairs all over Western and Central Europe. The old monastic scriptoria monastery workshops where monks copied texts by hand worked closely alongside the new presses, continuing to produce the luxury goods that movable type printing could not yet supply. Printing, however, was primarily aimed at a cheap mass sale. Although there was no competition between the technologies, there was rivalry between nations. The Italians made energetic and successful efforts to catch up with Germany. Their most successful scriptorium quickly imported two leading German printers to set up presses in their book-producing shop. German printers had the disadvantage of working with the complex typeface that the Italians sneeringly referred to as Gothic and that later became known as black letter. Outside Germany, readers found this typeface disagreeable. The Italians, on the other hand, had a clear typeface known as Roman that became the type of the future. Hence, although the Germans made use of the paper revolution to introduce movable type, the Italians went far to regain the initiative by their artistry. By 1500 there were printing firms in 60 German cities, but there were 150 presses in Venice alone. However, since many nations and governments wanted their own presses, the trade quickly became international. The cumulative impact of this industrial spread was spectacular. Before printing, only the very largest libraries, of which there were a dozen in Europe, had as many as 600 books. The total number of books on the entire continent was well under 100,000. But by 1500, after only 45 years of the printed book, there were 9 million in circulation. 49-3 Background for the Industrial Revolution. The Industrial Revolution had several roots, one of which was a commercial revolution that, beginning as far back as the 16th century, accompanied Europe's expansion overseas. Both exports and imports showed spectacular growth, particularly in England and France. An increasingly larger portion of the stepped-up commercial activity was the result of trade with overseas colonies. Imports included a variety of new beverages, spices, and ships' goods around the world and brought money flowing back. Europe's economic institutions, particularly those in England, were strong, had wealth available for new investment, and seemed almost to be waiting for some technological breakthrough that would expand their profit-making potential even more. The breakthrough came in Great Britain, where several economic advantages created a climate especially favorable to the encouragement of new technology. One was its geographic location at the crossroads of international trade. Internally, Britain was endowed with easily navigable natural waterway, which helped its trade and communication with the world. Beginning in the 1770s, it enjoyed a boom in canal building, which helped make its domestic market more accessible. Because water transportation was the cheapest means of carrying goods to market, canals reduced prices and thus increased consumer demand. Great Britain also had rich deposits of coal that fed the factories springing up in industrial and consumer goods. Another advantage was Britain's large population of rural, agricultural wage earners, as well as cottage workers, who had the potential of being more mobile than peasants of some other countries. Eventually they found their way to the cities or mining communities and provided the human power upon which the Industrial Revolution was built. The British people were also consumers. The absence of internal tariffs, such as those that existed in France or Italy or between the German states, made Britain the largest free trade area in Europe. Britain's relatively stable government also helped create an atmosphere conducive to industrial progress. Great Britain's better developed banking and credit system also helped speed the industrial progress, as did the fact that it was the home of an impressive array of entrepreneurs and inventors. Among them were a large number of nonconformists whose religious principles encouraged thrift and industry rather than luxurious living and who tended to pour their profits back into their business, thus providing the basis for continued expansion. A precursor to the Industrial Revolution was a revolution in agricultural techniques. Ideas about agricultural reform developed first in Holland, where as early as the mid-17th century, such modern methods as crop rotation, heavy fertilization, and diversification were all in use. Dutch peasant farmers were known throughout Europe for their agricultural innovations, but as British markets and opportunities grew, the English quickly learned from them. As early as the 17th century, the Dutch were helping them drain marshes and fens where, with the help of advanced techniques, they grew new crops. By the mid-18th century, new agricultural methods as well as selective breeding of livestock had caught on throughout the country. Much of the increased production was consumed by Great Britain's burgeoning population. At the same time, people were moving to the city, partly because of the enclosure movement, that is, the fencing of common fields and pastures in order to provide more compact, efficient privately held agricultural parcels that would produce more goods and greater profits. In the 16th century, enclosures were usually used for creating sheep pastures, but by the 18th century new farming techniques made it advantageous for large landowners to seek enclosures in order to improve agricultural production. Between 1714 and 1820, over 6 million acres of English land were enclosed. As a result, many small, independent farmers were forced to sell out simply because they could not compete. Non-landholding peasants and cottage workers, who worked for wages and grazed cows or pigs on the village common, were also hurt when the common was no longer available. It was such people who began to flock to the cities seeking employment and who found work in the factories that would transform the nation and the world. 48-to-1 Chinese population growth. Increases in population have usually been accompanied by an increase in trade. In the Western experience, commerce provided the conditions that allowed industrialization to get started, which in turn led to growth in science, technology, industry, transport, communications, social change, and the like that we group under the broad term of development. However, the massive increase in population that in Europe was at first attributed to industrialization starting in the 18th century occurred also and at the same period in China, even though there was no comparable industrialization. It is estimated that the Chinese population by 1600 was close to 150 million. The transition between the Ming and Qing dynasties may have seen a decline, but from 1741 to 1851 the annual figures rose steadily and spectacularly, perhaps beginning with 143 million and ending with 432 million. If we accept these totals, we are confronted with a situation in which the Chinese population doubled in the 50 years from 1790 to 1840. If, with greater caution, we assume lower totals in the early 18th century and only 400 million in 1850, we still face a startling fact: something like a doubling of the vast Chinese population in the century before Western contact, foreign trade, and industrialization could have had much effect. To explain this sudden increase, we cannot point to factors constant in Chinese society but must find conditions or a combination of factors that were newly effective in this period. Among these is the almost complete internal peace maintained under Manchu rule during the 18th century. There was also an increase in foreign trade through Guangzhou and some improvement of transportation within the empire. Control of disease, like the checking of smallpox by variolation, may have been important. But of most critical importance was the food supply. Confronted with a multitude of unreliable figures, economists have compared the population records with the aggregate data for cultivated land area and grain production in the 6 centuries since 1368. Assuming that China's population in 1400 was about 80 million, the economist Dwight Perkins concludes that its growth to 700 million or more in the 1960s was made possible by a steady increase in the grain supply, which evidently grew 5 or 6 times between 1400 and 1800 and rose another 50% between 1800 and 1965. This increase of food supply was due perhaps half to the increase of cultivated area, particularly by migration and settlement in the central and western provinces, and half to greater Productivity, the farmer's success in raising more crops per unit of land. This technological advance took many forms. One was the continual introduction from the south of earlier ripening varieties of rice, which made possible double cropping. New crops such as corn and sweet potatoes as well as peanuts and tobacco were introduced from the Americas. Corn, for instance, can be grown on the dry soil and marginal hill land of North China, where it is used for food, fuel, and fodder and provides something like 1/7 of the food energy available in the area. The sweet potato, growing in sandy soil and providing more food energy per unit of land than other crops, became the main food of the poor in much of the South China rice area. Productivity in agriculture was also improved by capital investments, first of all in irrigation. From 1400 to 1900, the total of irrigated land seems to have increased almost 3 times. There was also a gain in farm tools, draft animals, and fertilizer, to say nothing of the population growth itself, which increased half again as fast as cultivated land area and so increased the ratio of human hands available per unit of land. Thus the rising population was fed by a more intensive agriculture, applying more labor and fertilizer to the land. 47-1 Roman cultural influence on Britain. After the Roman Empire's conquest of Britain in the 1st century AD, the presence of administrators, merchants, and troops on British soil, along with the natural flow of ideas and goods from the rest of the empire, had an enormous influence on life in the British Isles. Cultural influences were of 3 types: the bringing of objects, the transfer of craft workers, and the introduction of massive civil architecture. Many objects were not art in even the broadest sense and comprised utilitarian items of clothing, utensils, and equipment. We should not underestimate the social status associated with such mundane possessions which had not previously been available. The flooding of Britain with red gloss pottery from Gaul, decorated with scenes from classical mythology, probably brought many into contact with the styles and artistic concepts of the Greco-Roman world for the first time, whether or not the symbolism was understood. Mass-produced goods were accompanied by fewer more aesthetically impressive objects such as statuettes. Such pieces perhaps first came with officials for their own religious worship. Others were then acquired by native leaders as diplomatic gifts or by purchase. Once seen by the natives, such objects created a fashion which rapidly spread through the province. In the most extreme instances, natives literally bought the whole package of Roman culture. The Fishborn Villa, built in the 3rd quarter of the 1st century AD, probably for the native client King Khajadubnis, amply illustrates his Roman pretensions. It was constructed in the latest Italian style with imported marbles and stylish mosaics. It was lavishly furnished with imported sculptures and other classical objects. A visitor from Rome would have recognized its owner as a participant in the contemporary culture of the empire, not at all provincial in taste. Even if those from the traditional families looked down on him, they would have been unable to dismiss him as uncultured. Although exceptional, this demonstrates how new cultural symbols bound provincials to the identify of the Roman world. Such examples established a standard to be copied. One result was an influx of craft worker, particularly those skilled in artistic media like stone carving, which had not existed before the conquest. Civilian workers came mostly from Gaul and Germany. The magnificent temple built beside the sacred spring at Bath was constructed only about 20 years after the conquest. Its detail shows that it was carved by artists from northeast Gaul. In the absence of a tradition of classical stone carving and building, the desire to develop Roman amenities would have been difficult to fulfill. Administrators thus used their personal contacts to put the Britons in touch with architects and masons. As many of the officials in Britain had strong links with Gaul, it is not surprising that early Roman Britain owes much to craft workers from that area. Local workshops did develop, and stylistically similar groups of sculpture show how skills in this new medium became widespread. Likewise, skills in the use of mosaic, wall painting, ceramic decoration, and metalworking developed throughout the province with the eventual emergence of characteristically Romano-British styles. This art had a major impact on the native peoples, and one of the most important factors was a change in the scale of buildings. Pre-Roman Britain was highly localized, with people rarely traveling beyond their own region. On occasion, large groups amassed for war or religious festivals, but society remained centered on small communities. Architecture of this era reflected this, with even the largest of the fortified towns and hill forts containing no more than clusters of medium-sized structures. The spaces inside even the largest roundhouses were modest, and the use of rounded shapes and organic building materials gave buildings a human scale. But the effect of Roman civil architecture was significant. The sheer size of space enclosed within buildings like the Basilica of London must have been astonishing. This was an architecture of dominance in which subject peoples were literally made to feel small by buildings that epitomized imperial power. Supremacy was accentuated by the unyielding straight lines of both individual buildings and planned settlements, since these two provided a marked contrast with the natural curvilinear shapes dominant in the native realm. 46:1 The origins of writing. It was in Egypt and Mesopotamia that civilization arose, and it is there that we find the earliest examples of that key feature of civilization, writing. These examples, in the form of inscribed clay tablets that date to shortly before 3000 BCE, have been discovered among the archaeological remains of the Sumerians, a gifted people settled in southern Mesopotamia. The Egyptians were not far behind in developing writing, but we cannot follow the history of their writing in detail because they used a perishable writing material. In ancient times, the banks of the Nile were lined with papyrus plants, and from the papyrus reeds the Egyptians made a form of paper. It was excellent in quality but, like any paper, fragile. Mesopotamia's rivers boasted no such useful reeds, but its land did provide good clay, and as a consequence the clay tablet became the standard material. Though clumsy and bulky, it has a virtue dear to archaeologists: it is durable. Fire, for example, which is death to papyrus paper or other writing materials such as leather and wood, simply bakes it hard, thereby making it even more durable. So when a conqueror set a Mesopotamian palace ablaze, he helped ensure the survival of any clay tablets in it. Clay, moreover, is cheap, and forming it into tablets is easy, factors that helped the clay tablet become the preferred writing material not only throughout Mesopotamia but far outside it as well, in Syria, Asia Minor, Persia, and even for a while in Crete and Greece. Excavators have unearthed clay tablets in all these lands. In the Near East they remained in use for more than 2.5 millennia, and in certain areas they lasted down to the beginning of the Common Era until finally yielding, once and for all, to more convenient alternatives. The Sumerians perfected a style of writing suited to clay. This script consists of simple shapes, basically just wedge shapes and lines that could easily be incised in soft clay with a reed or wooden stylus. Scholars have dubbed it cuneiform from the wedge-shaped marks that are its hallmark. Although the ingredients are merely wedges and lines, there are hundreds of combinations of these basic forms that stand for different sounds or words. Learning these complex signs required long training and much practice. Inevitably, literacy was largely limited to a small professional class, the scribes. The Akkadians conquered the Sumerians around the middle of the 3rd millennium BCE, and they took over the various cuneiform signs used for writing Sumerian and gave them sound and word values that fit their own language. The Babylonians and Assyrians did the same, and so did peoples in Syria and Asia Minor. The literature of the Sumerians was treasured throughout the Near East, and long after Sumerian ceased to be spoken, the Babylonians and Assyrians and others kept it alive as a literary language, the way Europeans kept Latin alive after the fall of Rome. For the scribes of these non-Sumerian languages, training was doubly demanding since they had to know the values of the various cuneiform signs for Sumerian as well as for their own language. The contents of the earliest clay tablets are simple notations of numbers of commodities, animals, jars, baskets, etc. Writing, it would appear, started as a primitive form of bookkeeping. Its use soon widened to document the multitudinous things and acts that are involved in daily life, from simple inventories of commodities to complicated governmental rules and regulations. Archaeologists frequently find clay tablets in batches. The batches, some of which contain thousands of tablets, consist for the most part of documents of the types just mentioned: bills, deliveries, receipts, inventories, loans, marriage contracts, divorce settlements, court judgments, and so on. These records of factual matters were kept in storage to be available for reference. They were, in effect, files, or, to use the term preferred by specialists in the ancient Near East, archives. Now and then these files include pieces of writing that are of a distinctly different order, writings that do not merely record some matter of fact but involve creative intellectual activity. They range from simple textbook material to literature, and they make an appearance very early, even from the 3rd millennium BCE. 44-2 The use of the camera obscura. The precursor of the modern camera, the camera obscura is a darkened enclosure into which light is admitted through a lens in a small hole. The image of the illuminated area outside the enclosure is thrown upside down as if by magic onto a surface in the darkened enclosure. This technique was known as long ago as the 5th century BC in China. Aristotle also experimented with it in the 4th century BC, and Leonardo da Vinci described it in his notebooks in 1490. In 1558, Giovanni Battista della Porta wrote in his 20-volume work Magia Naturalis instructions for adding a convex lens to improve the quality of the image thrown against a canvas or panel in the darkened area where its outlines could be traced. Later, portable camera obscuras were developed, with interior mirrors and drawing tables on which the artist could trace the image. For the artist, this technique allows forms and linear perspective to be drawn precisely as they would be seen from a single viewpoint. Mirrors were also used to reverse the projected images to their original positions. Did some of the great masters of painting, then, trace their images using a camera obscura? Some art historians are now looking for clues of artists' use of such devices. One of the artists whose paintings are being analyzed from this point of view is the great Dutch master, Jan Vermeer, who lived from 1632 to 1675. During the flowering of art and science in the Netherlands, including the science of optics, Vermeer produced only about 30 known paintings, including his famous The Art of Painting. The room shown in it closely resembles the room in other Vermeer paintings, with lighting coming from a window on the left, the same roof beams, and similar floor tiles, suggesting that the room was fitted with a camera obscura on the side in the foreground. The map hung on the opposite wall was a real map in Vermeer's possession, reproduced in such faithful detail that some kind of tracery is suspected. When one of Vermeer's paintings was x-rayed, it did not have any preliminary sketches on the canvas beneath the paint, but rather the complete image drawn in black and white without any trial sketches. Vermeer did not have any students, did not keep any records, and did not encourage anyone to visit his studio, facts that can be interpreted as protecting his secret use of a camera obscura. In recent times, the British artist David Hockney has published his investigations into the secret use of the camera obscura, claiming that for up to 400 years, many of Western art's great masters probably used the device to produce almost photographically realistic details in their paintings. He includes in this group Caravaggio, Hans Holbein, Leonardo da Vinci, Diego Velázquez, Jean-Auguste Dominique Ingres, Agnolo Bronzino, and Jan van Eyck. From an artist's point of view, Hockney observed that a camera obscura compresses the complicated forms of a three-dimensional scene into two-dimensional shapes that can easily be traced, and also increases the contrast between light and dark, leading to the chiaroscuro effect seen in many of these paintings. In Jan van Eyck's The Marriage of Giovanni Arnolfini and Giovanna Senemi, the complicated foreshortening in the chandelier and the intricate detail in the bride's garments are among the clues that Hockney thinks point to the use of the camera obscura. So what are we to conclude? If these artists did use a camera obscura, does that diminish their stature? Hockney argues that the camera obscura does not replace artistic skill in drawing and painting. In experimenting with it, he found that it is actually quite difficult to use for drawing, and he speculates that the artists probably combined their observations from life with tracing of shapes. 43-1 The Empire of Alexander the Great. In 334 BC, Alexander the Great took his Greek armies to the east and in only a few years completed his creation of an empire out of much of Southwest Asia. In the new empire, barriers to trade and the movement of peoples were removed, markets were put in touch with one another. In the next generation, thousands of Greek traders and artisans would enter this wider world to seek their fortunes. Alexander's actions had several important consequences for the region occupied by the empire. The first of these was the expansion of Greek civilization throughout the Middle East. Greek became the great international language. Towns and cities were established not only as garrisons, but as centers for the diffusion of Greek language, literature, and thought, particularly through libraries, as at Antioch. And the most famous of all, at Alexandria in Egypt, which would be the finest in the world for the next 1,000 years. Second, this internationalism spelled the end of the classical Greek city-state, the unit of government in ancient Greece, and everything it stood for. Most city-states had been quite small in terms of citizenry, and this was considered to be a good thing. The focus of life was the agora, the open marketplace where assemblies could be held and where issues of the day, as well as more fundamental topics such as the purpose of government or the relationship between law and freedom, could be discussed and decisions made by individuals in person. The philosopher Plato felt that the ideal city-state should have about 5,000 citizens, because to the Greeks it was important that everyone in the community should know each other. In decision-making, the whole body of citizens together would have the necessary knowledge in order generally to reach the right decision, even though the individual might not be particularly qualified to decide. The philosopher Aristotle, who lived at a time when the city-state system was declining, believed that a political entity of 100,000 simply would not be able to govern itself. This implied that the city-state was based on the idea that citizens were not specialists but had multiple interests and talents, each a so-called jack-of-all-trades who could engage in many areas of life and politics. It implied a respect for the wholeness of life and a consequent dislike of specialization. It implied economic and military self-sufficiency. But with the development of trade and commerce in Alexander's empire came the growth of cities. It was no longer possible to be a jack-of-all-trades. One now had to specialize, and with specialization came professionalism. There were getting to be too many persons to know. An easily observable community of interests was being replaced by a multiplicity of interests. The city-state was simply too small time. Third, Greek philosophy was opened up to the philosophy and religion of the East. At the peak of the Greek city-state, religion played an important part. Its gods, such as Zeus, father of the gods, and his wife Hera, were thought of very much as being like human beings but with superhuman abilities. Their worship was linked to the rituals connected with one's progress through life, birth, marriage, and death, and with invoking protection against danger, making prophecies, and promoting healing, rather than to any code of behavior. Nor was there much of a theory of afterlife. Even before Alexander's time, a life spent in the service of their city-state no longer seemed ideal to Greeks. The Athenian philosopher Socrates was the first person in Greece to propose a morality based on individual conscience rather than the demands of the state, and for this he was accused of not believing in the city's gods and so corrupting the youth, and he was condemned to death. Greek philosophy, or even a focus on conscience, might complement religion but was no substitute for it, and this made Greeks receptive to the religious systems of the Middle East, even if they never adopted them completely. The combination of the religious instinct of Asia with the philosophic spirit of Greece spread across the world in the era after Alexander's death, blending the culture of the Middle East with the culture of Greece. 41:1 Navajo art. The Navajo, a Native American people living in the southwestern United States, live in small scattered settlements. In many respects, such as education, occupation, and leisure activities, their life is like that of other groups that contribute to the diverse social fabric of North American culture in the 21st century. At the same time, they have retained some traditional cultural practices that are associated with particular art forms. For example, the most important traditional Navajo rituals include the production of large floor paintings. These are actually made by pouring thin, finely controlled streams of colored sands or pulverized vegetable and mineral substances, pollen, and flowers in precise patterns on the ground. The largest of these paintings may be up to 5.5 meters in diameter and cover the entire floor of a room. Working from the inside of the design outward, the Navajo artist and his assistants will sift the black, white, bluish-gray, orange, and red materials through their fingers to create the finely detailed imagery. The paintings and chants used in the ceremonies are directed by well-trained artists and singers who enlist the aid of spirits who are impersonated by masked performers. The 24 known Navajo chants can be represented by up to 500 sand paintings. These complex paintings serve as memory aids to guide the singers during the performance of the ritual songs, which can last up to 9 days. The purpose and meaning of the sand paintings can be explained by examining one of the most basic ideals of Navajo society, embodied in their word hazo. It coexists with haxo in a world where opposing forces of dynamism and stability create constant change. When the world, which was created in beauty, becomes ugly and disorderly, the Navajo gather to perform rituals with songs and make sand paintings to restore beauty and harmony to the world. Some illness is itself regarded as a type of disharmony. Thus, the restoration of harmony through a ceremony can be part of a curing process. Men make sand paintings that are accurate copies of paintings from the past. The songs sung over the paintings are also faithful renditions of songs from the past. By recreating these arts, which reflect the original beauty of creation, the Navajo bring beauty to the present world. As relative newcomers to the Southwest, a place where their climate, neighbors, and rulers could be equally inhospitable, the Navajo created these art forms to affect the world around them, not just through the recounting of the action symbolized, but through the beauty and harmony of the artworks themselves. The paintings generally illustrate ideas and events from the life of a mythical hero, who, after being healed by the gods, gave gifts of songs and paintings. Working from memory, the artists recreate the traditional form of the image as accurately as possible. The Navajo are also world famous for the designs on their woven blankets. Navajo women own the family flocks, control the shearing of the sheep, the carding, the spinning, and dyeing of the thread, and the weaving of the fabrics. While the men who make faithful copies of sand paintings from the past represent the principle of stability in Navajo thought, women embody dynamism and create new designs for every weaving they make. Weaving is a paradigm of the creativity of a mythic ancestor named Spider-Woman who wove the universe as a cosmic web that united earth and sky. It was she who, according to legend, taught Navajo women how to weave. As they prepare their materials and weave, Navajo women imitate the transformations that originally created the world. Working on their looms, Navajo weavers create images through which they experience harmony with nature. It is their means of creating beauty and thereby contributing to the beauty, harmony, and healing of the world. Thus, weaving is a way of seeing the world and being part of it. 40-1 Ancient Athens. One of the most important changes in Greece during the period from 800 BC to 500 BC was the rise of the polis, or city-state, and each polis developed a system of government that was appropriate to its circumstances. The problems that were faced and solved in Athens were the sharing of political power between the established aristocracy and the emerging other classes, and the adjustment of aristocratic ways of life to the ways of life of the new polis. It was the harmonious blending of all of these elements that was to produce the classical culture of Athens. Entering the polis age, Athens had the traditional institutions of other Greek proto-democratic states, an assembly of adult males, an aristocratic council, and annually elected officials. Within this traditional framework, the Athenians, between 600 BC and 450 BC, evolved what Greeks regarded as a fully fledged democratic constitution, though the right to vote was given to fewer groups of people than is seen in modern times. The first steps toward change were taken by Solon in 594 BC, when he broke the aristocracy's stranglehold on elected offices by establishing wealth rather than birth as the basis of office holding, abolishing the economic obligations of ordinary Athenians to the aristocracy, and allowing the assembly to overrule the decisions of local courts in certain cases. The strength of the Athenian aristocracy was further weakened during the rest of the century by the rise of a type of government known as a tyranny, which is a form of interim rule by a popular strongman. The Pisistratids, as the succession of tyrants were called, strengthened Athenian central administration at the expense of the aristocracy by appointing judges throughout the region, producing Athens' first national coinage, and adding and embellishing festivals that tended to focus attention on Athens rather than on local villages of the surrounding region. By the end of the century, the time was ripe for more change. The tyrants were driven out, and in 508 BC a new reformer, Callisto, gave final form to the developments reducing aristocratic control already underway. Callisto's principal contribution to the creation of democracy at Athens was to complete the long process of weakening family and clan structures, especially among the aristocrats, and to set in their place locality-based corporations called demes, which became the point of entry for all civic and most religious life in Athens. Out of the demes were created 10 artificial tribes of roughly equal population. From the demes, by either election or selection, came 500 members of a new council, 6,000 jurors for the courts, 10 generals, and hundreds of commissioners. The assembly was sovereign in all matters but in practice delegated its power to subordinate bodies such as the council, which prepared the agenda for the meetings of the assembly, and courts, which took care of most judicial matters. Various committees acted as an executive branch, implementing policies of the assembly and supervising, for instance, the food and water supplies in public buildings. This wide-scale participation by the citizenry in the government distinguished the democratic form of the Athenian polis from other less liberal forms. The effect of Cleisthenes' reforms was to establish the superiority of the Athenian community as a whole over local institutions without destroying them. National politics rather than local or demi-politics became the focal point. At the same time, entry into national politics began at the demi-level and gave local loyalty a new focus, Athens itself. Over the next 2 centuries, the implications of Cleisthenes' reforms were fully exploited. During the 5th century BC, the Council of 500 was extremely influential in shaping policy. In the next century, however, it was the mature assembly that took on decision-making responsibility. By any measure other than that of the aristocrats, who had been upstaged by the supposedly inferior people, the Athenian democracy was a stunning success. Never before, or since, have so many people been involved in the serious business of self-governance. It was precisely this opportunity to participate in public life that provided a stimulus for the brilliant unfolding of classical Greek culture. 39-1 Early writing systems. Scholars agree that writing originated somewhere in the Middle East, probably Mesopotamia, around the 4th millennium BCE. It is from the great libraries and word hoards of these ancient lands that the first texts emerged. They were written on damp clay tablets with a wedged stick. Since the Latin word for wedge is cunea, the texts are called cuneiform. The clay tablets usually were not fired. Sun drying was probably reckoned enough to preserve the text for as long as it was being used. Fortunately, however, many tablets survived because they were accidentally fired when the buildings they were stored in burned. Cuneiform writing lasted for some 3,000 years, in a vast line of succession that ran through Sumer, Akkad, Assyria, Nineveh, and Babylon, and preserved for us 15 languages in an area represented by modern-day Iraq, Syria, and western Iran. The oldest cuneiform texts recorded the transactions of tax collectors and merchants, the receipts and bills of sale of an urban society. They had to do with things like grain, goats, and real estate. Later, Babylonian scribes recorded the laws and kept other kinds of records. Knowledge conferred power. As a result, the scribes were assigned their own goddess, Nisaba, later replaced by the god Nabu of Borsippa, whose symbol is neither weapon nor dragon but something far more fearsome, the cuneiform stick. Cuneiform texts on science, astronomy, medicine, and mathematics abound, some offering astoundingly precise data. One tablet records the speed of the moon over 248 days, another documents an early sighting of Halley's Comet, from September 22 to September 28, 164 BCE. More esoteric texts attempt to explain old Babylonian customs, such as the procedure for curing someone who was ill, which included rubbing tar and gypsum on the sick person's door and drawing a design at the foot of the person's bed. What is clear from the vast body of texts is that scribes took pride in their writing and knowledge. The foremost cuneiform text, the Babylonian epic of Gilgamesh, deals with humankind's attempts to conquer time. In it, Gilgamesh, king and warrior, is crushed by the death of his best friend and so sets out on adventures that prefigure mythical heroes of ancient Greek legends such as Hercules. His goal is not just to survive his ordeals but to make sense of this life. Remarkably, versions of Gilgamesh span 1,500 years, between 2100 BC and 600 BCE, making the story the epic of an entire civilization. The ancient Egyptians invented a different way of writing and a new substance to write on: a papyrus, a precursor of paper, made from a wetland plant. The Greeks had a special name for this writing, hieroglyphic, literally sacred writing. This, they thought, was language fit for the gods, which explains why it was carved on walls of pyramids and other religious structures. Perhaps hieroglyphics are Egypt's great contribution to the history of writing. Hieroglyphic wiring, in use from 3100 BC until 394 CE, resulted in the creation of texts that were fine art as well as communication. Egypt gave us the tradition of the scribe not just as educated person but as artist and calligrapher. Scholars have detected some 6,000 separate hieroglyphic characters in use over the history of Egyptian writing, but it appears that never more than 1,000 were in use during any one period. It still seems a lot to recall, but what was lost in efficiency was more than made up for in the beauty and richness of the texts. Writing was meant to impress the eye with the vastness of creating itself. Each symbol or glyph, the flowering reed, the owl, the quail chick, etc., was a tiny work of art. Manuscripts were compiled with an eye to the overall design. Egyptologists have noticed that the glyphs that constitute individual words were sometimes shuffled to make the text more pleasing to the eye with little regard for sound or sense. 35-2 The development of social complexity. For most of human history, we have foraged for food. Small nomadic groups could easily supply the necessities for their families. No one needed more, and providing for more than one's needs made little sense. The organization of such societies could be rather simple, revolving around age and gender categories. Such societies likely were largely egalitarian, beyond distinctions based on age and gender. Virtually all people had equivalent rights, status, and access to resources. Archaeologist Donald Henry suggests that the combination of a rich habitat and sedentism led to a dramatic increase in human population. In his view, nomadic, simple foragers have relatively low levels of fertility. Their high-protein, low-carbohydrate diets result in low body fat levels, which are commonly associated with low fertility in women. High levels of physical activity and long periods of nursing, which are common among modern simple foragers, probably also contributed to low levels of female fertility if they were likewise common among ancient foragers. In Henry's view, the adoption of a more settled existence in areas with abundant food resources would have contributed to higher fertility levels among the sedentary foragers. A diet higher in wild cereals produces proportionally more body fat, leading to higher fertility among women. Cereals, which are easy to digest, would have supplemented and then replaced mother's milk as the primary food for older infants. Since women are less fertile when they are breastfeeding, substituting cereals for mother's milk would have resulted in closer spacing of births and the potential for a greater number of live births for each woman. A more sedentary existence may also have lowered infant mortality and perhaps increased longevity among the aged. These more vulnerable members of society could safely stay in a fixed village rather than be forced regularly to move great distances as part of a nomadic existence, with its greater risk of accidents and trauma. All of these factors may have resulted in a trend of increasing size among some local human populations in the Holocene. Given sufficient time, even in very rich habitats, human population size can reach carrying capacity, the maximum population an area can sustain within the context of a given subsistence system. And human population growth is like a runaway tram. Once it picks up speed, it is difficult to control. So even after reaching an area's carrying capacity, Holocene human populations probably continued to grow in food-rich regions, overshooting the ability of the territory to feed the population, again within the context of the same subsistence strategy. In some areas, small changes in climate or minor changes in plant characteristics may have further destabilized local economies. One possible response to surpassing the carrying capacity of a region is for a group to exploit adjoining land. However, good land may itself be limited, for example, within the confines of a river valley where neighbors are in the same position, having filled up the whole of the desirable habitat available in their home territories. Expansion is also problematic. Impinging on the neighbor's territory can lead to conflict, especially when they too are up against the capacity of the land to provide enough food. Another option is to stay in the same area but to shift and intensify the food quest there. The impulse to produce more food to feed a growing population was satisfied in some areas by the development of more complex subsistence strategies involving intensive labor and requiring more cooperation and greater coordination among the increasing numbers of people. This development resulted in a change in the social and economic equations that defined those societies. Hierarchies that did not exist in earlier foraging groups but that were helpful in structuring Cooperative labor and in organizing more complex technologies probably became established, even before domestication and agriculture, as pre-Neolithic societies reacted to the population increase. 52 to 1 stream deposit. A large, swift stream or river can carry all sizes of particles, from clay to boulders. When the current slows down, its competence decreases and the stream deposits the largest particles in the streambed. If current velocity continues to decrease as a flood wanes, for example, finer particles settle out on top of the large ones. Thus, a stream sorts its sediment according to size. A waning flood might deposit a layer of gravel overlain by sand and finally topped by silt and clay. Streams also sort sediment in the downstream direction. Many mountain streams are choked with boulders and cobbles, but far downstream, their deltas are composed mainly of fine silt and clay. This downstream sorting is curious because stream velocity generally increases in the downstream direction. Competence increases with velocity, so a river should be able to transport larger particles than its tributaries carry. One explanation for downstream sorting is that abrasion wears away the boulders and cobbles to sand and silt as the sediment moves downstream over the years. Thus, only the fine sediment reaches the lower parts of most rivers. A stream deposits its sediment in 3 environments. Alluvial fans and deltas form where stream gradient suddenly decreases as a stream enters a flat plain, a lake, or the sea. Floodplain deposits accumulate on a floodplain adjacent to the stream channel, and channel deposits form in the stream channel itself. Bars, which are elongated mounds of sediment, are transient features that form in the stream channel and on the banks. They commonly form in one year and erode the next. Rivers used for commercial navigation must be recharged frequently because bars shift from year to year. Imagine a winding stream. The water on the outside of the curve moves faster than the water on the inside. The stream erodes its outside bank because the current's inertia drives it into the outside bank. At the same time, the slower water on the inside point of the bend deposits sediment, forming a point bar. A mid-channel bar is a sandy and gravelly deposit that forms in the middle of a stream channel. Most streams flow in a single channel. In contrast, a braided stream flows in many shallow, interconnecting channels. A braided stream forms where more sediment is supplied to a stream than it can carry. The stream dumps the excess sediment, forming mid-channel bars. The bars gradually fill a channel, forcing the stream to overflow its banks and erode new channels. As a result, a braided stream flows simultaneously in several channels and shifts back and forth across its floodplain. Braided streams are common in both deserts and glacial environments because both produce abundant sediment. A desert yields large amounts of sediment because it has little or no vegetation to prevent erosion. Glaciers grind bedrock into fine sediment, which is carried by streams flowing from the melting ice. If a steep mountain stream flows onto a flat plain, its gradient and velocity decrease sharply. As a result, it deposits most of its sediment in a fan-shaped mound called an alluvial fan. Alluvial fans are common in many arid and semi-arid mountainous regions. A stream also slows abruptly where it enters the still water of a lake or ocean. The sediment settles out to form a nearly flat landform called a delta. Part of the delta lies above water level, and the remainder lies slightly below water level. Deltas are commonly fan-shaped, resembling the Greek letter delta. Both deltas and alluvial fans change rapidly. Sediment fills channels, which are then abandoned while new channels develop as in a braided stream. As a result, a stream feeding a delta or fan splits into many channels called distributaries. A large delta may spread out in this manner until it covers thousands of square kilometers. Most fans, however, are much smaller, covering a fraction of a square kilometer to a few square kilometers. The Mississippi River has flowed through 7 different delta channels during the past 5,000 to 6,000 years. But in recent years, engineers have built great systems of levees in attempts to stabilize the channels. 49 to 1 Ancient coastlines. Information on past climates is of primary relevance to archaeology because of what it tells us about the effects on the land and on the resources that people needed to survive. The most crucial effect of climate was on the sheer quantity of land available in each period, measurable by studying ancient coastlines. These have changed constantly through time, even in relatively recent periods, as can be seen from the Neolithic stone circle of Aire-Lonnic, in Brittany, France, or medieval villages in East Yorkshire. England, that have tumbled into the sea in the last few centuries as the North Sea gnaws its way westward and erodes the cliffs. Conversely, silts deposited by rivers sometimes push the sea farther back, creating new land, as at Ephesus in western Turkey, a port on the coast in Roman times but today some 5 kilometers inland. Nevertheless, for archaeologists concerned with the long periods of time of the Paleolithic period, there are variations in coastlines of much greater magnitude to consider. The expansion and contraction of the continental glaciers caused huge and uneven rises and falls in sea levels worldwide. When the ice sheets grew, the sea level would drop as water became locked up in the glaciers. When the ice melted, the sea level would rise again. Falls in sea level often exposed a number of important land bridges, such as those linking Alaska to Northeast Asia and Britain to Northwest Europe. A phenomenon with far-reaching effects not only on human colonization of the globe but also on the environment as a whole. The flora and fauna of isolated or insular areas were radically and often irreversibly affected. Between Alaska and Asia today lies the Bering Strait, which is so shallow that a fall in sea level of only 4 meters would turn it into a land bridge. When the ice sheets were at their greatest extent some 18,000 years ago, it is thought that the fall was about 120 meters, which therefore created not merely a bridge but a vast plain 1,000 kilometers from the north to the south, which has been called Beringia. The existence of Beringia is one of the crucial pieces of evidence in the continuing debate about the likely route and date of human colonization of the New World. The assessment of past rises and falls in sea level requires study of submerged land surfaces off the coast and of raised or elevated beaches on land. Raised beaches are remnants of former coastlines at higher levels relative to the present shoreline, invisible, for instance, along the Californian coast north of San Francisco. The height of a raised beach above the present shoreline, however, does not generally give a straightforward indication of the height of a former sea level. In the majority of cases, the beaches lie at a higher level because the land has been raised up through isostatic uplift or tectonic movement. Isostatic uplift of the land occurs when the weight of ice is removed as temperatures rise, as at the end of an ice age. It has affected coastlines, for example, in Scandinavia, Scotland, Alaska, and Newfoundland during the post-glacial period. Tectonic movements involve displacements in the plates that make up Earth's crust. Middle and late Pleistocene raised beaches in the Mediterranean are one instance of such movements. Raised beaches often consist of areas of sand, pebbles, or dunes, sometimes containing seashells or piles of debris comprising shells and bones of marine animals used by humans. In Tokyo Bay, for example, shell mounds of the Jomon period marked the position of the shoreline at a time of maximum inundation by the sea, when, through tectonic movement, the sea was 3 to 5 meters higher in relation to the contemporary landmass of Japan than at present. Analysis of the shells themselves has confirmed the changes in marine topography, for it is only during the maximum phase that subtropical species of mollusk are present, indicating a higher water temperature. 48-3 Climate and urban development. For more than 100 years, it has been known that cities are generally warmer than surrounding rural areas. This region of city warmth, known as the urban heat island, can influence the concentration of air pollution. However, before we look at its influence, let's see how the heat island actually forms. The urban heat island is due to industrial and urban development. In rural areas, a large part of the incoming solar energy is used in evaporating water from vegetation and soil. In cities, where less vegetation and exposed soil exist, the majority of the sun's energy is absorbed by urban structures and asphalt. Hence, during warm daylight hours, less evaporative cooling in cities allows surface temperatures to rise higher than in rural areas. The cause of the urban heat island is quite involved. Depending on the location, time of year, and time of day, any or all of the following differences between cities and their surroundings can be important: albedo, surface roughness, emissions of heat, emissions of moisture, and emissions of particles that affect net radiation and the growth of cloud droplets. At night, the solar energy is slowly released into the city air. Additional city heat is given off at night by vehicles and factories, as well as by industrial and domestic heating and cooling units. The release of heat energy is retarded by the tall vertical city walls that do not allow infrared radiation to escape as readily as does the relatively level surface of the surrounding countryside. The slow release of heat tends to keep nighttime city temperatures higher than those of the faster cooling. Rural areas. Overall, the heat island is strongest at night when compensating sunlight is absent, during the winter, when nights are longer and there is more heat generated in the city, and when the region is dominated by a high-pressure area with light winds, clear skies, and less humid air. Over time, increasing urban heat islands affect climatological temperature records, producing artificial warming and climatic records taken in cities. This warming, therefore, must be accounted for in interpreting climate change over the past century. The constant outpouring of pollutants into the environment may influence the climate of the city. Certain particles reflect solar radiation, thereby reducing the sunlight that reaches the surface. Some particles serve as nuclei upon which water and ice form. Water vapor condenses onto these particles when the relative humidity is as low as 70%, forming haze that greatly reduces visibility. Moreover, the added nuclei increase the frequency of city fog. Studies suggest that precipitation may be greater in cities than in the surrounding countryside. This phenomenon may be due in part to the increased roughness of city terrain, brought on by large structures that cause surface air to slow and gradually converge. This piling up of air over the city then slowly rises, much like toothpaste does when its tube is squeezed. At the same time, city heat warms the surface air, making it more unstable, which enhances rising air motions, which, in turn, aids in forming clouds and thunderstorms. This process helps explain why both tend to be more frequent over cities. On clear still nights when the heat island is pronounced, a small thermal low-pressure area forms over the city. Sometimes a light breeze, called a country breeze, blows from the countryside into the city. If there are major industrial areas along the outskirts, pollutants are carried into the heat of town, where they tend to concentrate. Such an event is especially probable if vertical mixing and dispersion of pollutants are inhibited. Pollutants from urban areas may even affect the weather downwind from them. 43-2 The origin of petroleum. Petroleum is defined as a gaseous, liquid, and semi-solid naturally occurring substance that consists chiefly of hydrocarbons. Petroleum is therefore a term that includes both oil and natural gas. Petroleum is nearly always found in marine sedimentary rocks. In the ocean, microscopic phytoplankton and bacteria are the principal sources of organic matter that is trapped and buried in sediment. Most of the organic matter is buried in clay that is slowly converted to a fine-grained sedimentary rock known as shale. During this conversion, organic compounds are transformed to oil and natural gas. Sampling on the continental shelves and along the base of the continental slopes has shown that fine muds beneath the seafloor contain up to 8% organic matter. Two additional kinds of evidence support the hypothesis that petroleum is a product of the decomposition of organic matter. Oil possesses optical properties known only in hydrocarbons derived from organic matter, and oil contains nitrogen and certain compounds believed to originate only in living matter. A complex sequence of chemical reactions is involved in converting the original solid organic matter to oil and gas, and additional chemical changes may occur in the oil and gas even after they have formed. It is now well established that petroleum migrates through aquifers and can become trapped in reservoirs. Petroleum migration is analogous to groundwater migration. When oil and gas are squeezed out of the shale in which they originated and enter a body of sandstone or limestone somewhere above, they migrate readily because sandstones and limestones are much more permeable than any shale. The force of molecular attraction between oil and quartz or carbonate minerals is weaker than that between water and quartz or carbonate minerals. Hence, because oil and water do not mix, water remains fastened to the quartz or carbonate grains, while oil occupies the central parts of the larger openings in the porous sandstone or limestone. Because oil is lighter than water, it tends to glide upward past the carbonate and quartz-held water. In this way, oil becomes segregated from the water. When it encounters a trap, it can form a pool. Most of the petroleum that forms in sediments does not find a suitable trap and eventually makes its way, along with groundwater, to the surface of the sea. It is estimated that no more than 0.1% of all the organic matter originally buried in a sediment is eventually trapped in an oil pool. It is not surprising, therefore, that the highest ratio of oil and gas pools to volume of sediment is found in rock no older than 2.5 million years, young enough so that little of the petroleum has leaked away, and that nearly 60% of all oil and gas discovered so far has been found in strata that formed in the last 65 million years. This does not mean that older rocks produce less petroleum, it simply means that oil in older rocks has had a longer time in which to leak away. How much oil is there in the world? This is an extremely controversial question. Many billions of barrels of oil have already been pumped out of the ground. A lot of additional oil has been located by drilling but is still waiting to be pumped out. Possibly a great deal more oil remains to be found by drilling. Unlike coal, the volume of which can be accurately estimated, the volume of undiscovered oil can only be guessed at. Guesses involve the use of accumulated experience from a century of drilling. Knowing how much oil has been found in an intensively drilled area, such as eastern Texas, experts make estimates of probable volumes in other regions where rock types and structures are similar to those in eastern Texas. Using this approach and considering all the sedimentary basins of the world, experts estimate that somewhere between 1,500 and 3,000 billion barrels of oil will eventually be discovered. 43-3 El Niño. The cold Humboldt Current of the Pacific Ocean flows toward the equator along the coasts of Ecuador and Peru in South America. When the current approaches the equator, the westward flowing trade winds cause nutrient-rich cold water along the coast to rise from deeper depths to more shallow ones. This upwelling of water has economic repercussions. Fishing, especially for anchovies, is a major local industry. Every year during the months of December and January, a weak, warm countercurrent replaces the normally cold coastal waters. Without the upwelling of nutrients from below to feed the fish, fishing comes to a standstill. Fishers in this region have known the phenomenon for hundreds of years. In fact, this is the time of year they traditionally set aside to tend to their equipment and await the return of cold water. The residents of the region have given this phenomenon the name of El Niño, which is Spanish for the child, because it occurs at about the time of the celebration of birth of the Christ child. While the warm water countercurrent usually lasts for 2 months or less, there are occasions when the disruption to the normal flow lasts for many months. In these situations, water temperatures are raised not just along the coast, but for thousands of kilometers offshore. Over the last few decades, the term El Niño has come to be used to describe these exceptionally strong episodes and not the annual event. During the past 60 years, at least 10 El Niños have been observed. Not only do El Niños affect the temperature of the equatorial Pacific, but the strongest of them impact global weather. The processes that interact to produce an El Niño involve conditions all across the Pacific, not just in the waters off South America. Over 60 years ago, Sir Gilbert Walker, a British scientist, discovered a connection between surface pressure readings at weather stations on the eastern and western sides of the Pacific. He noted that a rise in atmospheric pressure in the eastern Pacific is usually accompanied by a fall in pressure in the western Pacific and vice versa. He called this seesaw pattern the Southern Oscillation. It was later realized that there is a close link between El Niño and the Southern Oscillation. In fact, the link between the two is so great that they are often referred to jointly as ENSO. During a typical year, the Eastern Pacific has a higher pressure than the Western Pacific does. This east-to-west pressure gradient enhances the trade winds over the equatorial waters. This results in a warm surface current that moves east to west at the equator. The Western Pacific develops a thick, warm layer of water while the Eastern Pacific has the cold Humboldt Current enhanced by upwelling. However, in other years the Southern Oscillation, for unknown reasons, swings in the opposite direction, dramatically changing the usual conditions described above, with pressure increasing in the Western Pacific and decreasing in the Eastern Pacific. This change in the pressure gradient causes the trade winds to weaken or, in some cases, to reverse. This then causes the warm water in the Western Pacific to flow eastward, increasing sea surface temperatures in the Central and Eastern Pacific. The eastward shift signals the beginning of an El Niño. Scientists try to document as many past El Niño events as possible by piecing together bits of historical evidence, such as sea surface temperature records, daily observations of atmospheric pressure and rainfall, fisheries records from South America, and the writings of Spanish colonists dating back to the 15th century. From such historical evidence, we know that El Niños have occurred as far back as records go. It would seem that they are becoming more frequent. Records indicate that during the 16th century, an El Niño occurred on average every 6 years. Evidence gathered over the past few decades indicates that El Niños are now occurring on average a little over every 2 years. Even more alarming is the fact that they appear to be getting stronger. The 1997 to 1998 El Niño brought copious and damaging rainfall to the southern United States, from California to Florida. Snowstorms in the northeast portion of the United States were more frequent and intense than in most years. 36-3 Industrial Melanism. The case of the peppered moth. The idea of natural selection is that organisms in a species that have characteristics favoring survival are most likely to survive and produce offspring with the same characteristics. Because the survival of organisms